Good morning. Let's get started. We have been talking about importance for the multinomial distribution. And in the last class, we introduced the probability mass function for the multinomial observations. And as you see here, the very first line, you see the multinomial probability mass function. And so your observed data are N1, N2, Nc, assuming there are C mutually exclusive and exhaustive classes, and N1, N2, N sub C are the counts for these classes. Corresponding probabilities are pi 1, pi 2, pi c. In the probability mass function for observing N1 counts for category 1, N2 counts for category 2, so on and so forth, can be obtained through this formula. N factorial over N1 factorial, N2 factorial, dot, 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 Nc factorial. It will be multiplied with pi 1 to the power N1, pi 2 to the power N2, multiplied with pi c to the power Nc. This is the formula. Now the question is, in a real life scenario, when you do not know pi 1, pi 2, pi c, the probabilities for each category, how do you estimate them from the observed data? Your observed data are the counts N1, N2, N sub C. So then the corresponding probability estimates, they are actually the maximum likelihood estimates, are the relative frequencies for that particular class. For example, if you are interested in estimating pi 1, then pi 1 hat will be N1 over N. N1 is the number of counts in category 1 divided by the total number of counts in your observations, set of observations. Likewise, you can get pi I hat equal to Ni over N. And some properties of the estimators are as follows. Often we are interested in knowing if the estimator is unbiased. So in this case, they are unbiased. That means the expected value of the maximum likelihood estimator of the ith category, which is pi I hat, the expected value is the true probability of that category, pi I. Variance of pi I hat is pi I times 1 minus pi I over N. N is the number of observations in your data. And the correlation between pi I hat and pi j hat is given by this expression. Now, this multinomial distribution, what is the use of it? Often it is used for testing goodness of fit. And this is one scenario. Suppose that the random variables, capital N, which are N1 containing the counts N1 into N sub C, as a multinomial distribution. And that multinomial distribution we denote it by mult. N is the total count, and pi 1, pi 2, pi c are the corresponding success probabilities. Now, C is the number of mutually exclusive categories one can have. So if you sum the success probabilities over the categories, it will add up to 1. And we wish to test the null hypothesis. Suppose we want to check whether pi 1, the success probability for category 1 equal to pi 1, 0, success probability for category 2 is pi 2, 0, and success probability for category C is equal to pi C, 0. So these values, pi 1, 0, pi 2, 0, pi C, 0, these are given values. And alternative is that at least some of pi i's are not equal to pi I 0. This screen is okay. Now let me try dividing the screen into two parts. One part, and another part I'm going to open Paint where I can write things. I will keep it on this side, on the right side. So it will work. My point is, we are often interested in testing this hypothesis that success probability for category 1 equal to pi 1 0, and you specify the success probability for all the categories pi c equal to pi c 0. This guy is unknown, pi 1 0. So these guys are known, pi 1 0, pi c 0. These are specified by users. And the alternative is at least one of the condition is violated. These conditions, okay? These conditions are specified under the null, and the alternative is at least one of them is violated. Now, how do you test that hypothesis? This is, we test it through Pearson chi-square test. And the test statistics looks like the following. This expression, test statistics expression is given here. Chi-square is the statistics expression is equal to sum over all the categories, and then for every category we first calculate mu I, which is the expected count of that category, ith category, for example, mu sub I under the null hypothesis, and ni is the observed number of counts in that category. So take the difference. So you take the difference ni minus mu I, square it, and divide it by mu I. It is exactly same as whether you can write it in many different ways, but it is ni minus mu I square over mu I. And this guy, chi-square, is a statistics, follows the chi-square distribution with degrees of freedom, c minus 1. When sample size is large enough, and so we reject the null hypothesis if the value of this chi-square is very large. Now, how large? It depends on the level of significance. At what level we want to test the hypothesis. For instance, if we want to test the hypothesis at let's say 5% level, so if we test H0 at alpha equal to 0.05, then we reject H0 if the statistic value, observed I squared is greater than the upper alpha percentile of the chi-square distribution with degrees of freedom C minus 1. So here alpha equal to 0.05, so it will be 0.05. What it means, this is upper fifth percentile. So you think about, this is the chi-square distribution, 0 all the way up to infinity. And if you look at the chi-square density, it looks like this. So this value, this guy, is the value, coordinate value, chi-square 0.05, freedom C minus 1. This is what? This is the density function. This is the density function of chi-square distribution with degrees of freedom C minus 1. And this ordinate value such that the area under the density curve, which is above this point, 0.05. And you can get that value easily from R. The idea. If you want to test the hypothesis at alpha equal to 1%, instead of 0.05, we can set alpha equal to 0.05. In that case, it would be 0.01. So if we test alpha equal to 0.01 level, then we reject H0 if the observed chi-square is greater than chi-square 0.01 with degrees of freedom C minus 1. And in this case, it will be chi-square 1 C minus 1 is this ordinate value such that the area under the density curve on the right side of this ordinate value is 0.01. The idea. Now this test, we carried out this test using Pearson chi-square test statistics. One can also apply likelihood ratio test in this context. And the general form of the likelihood ratio test is you calculate generalized likelihood ratio denoted by this notation. We call it capital lambda notation, which is maximized likelihood under null hypothesis divided by the maximized likelihood under the alternative hypothesis. And the test statistics is given at the bottom line is the test statistics. So here, the statistics is g squared, which is minus 2 times log, and we reject H0 or our statistics is greater than, again, it follows chi-square distribution with degrees of freedom C-1. The test statistics has a chi-square distribution under the null hypothesis. So we reject again if G square greater than upper alpha percentile of the chi-square distribution with degrees of freedom C-1. If G square, the test statistics is larger than this threshold, then we reject it. What if our test statistics is not larger than this threshold? Then we fail to reject the null hypothesis and conclude that we do not have sufficient evidence in favor of the alternative hypothesis. Okay. Some comments that for this problem, for the multinomial problem, our G squared statistics takes the following form. So if you take the log of G squared statistics, it turned out to be 2 times and it is in I of in I over mu I. And the question is, which one should we use? Pearson chi-square test or likelihood ratio test? So it says that Pearson chi-square test and likelihood ratio test both have similar values, particularly for large sample. Both statistics will be equal to 0 if Ni equal to mu I for all I. That means observed count and expected counts are the same. And generally, both statistics will lead to the same inference for any given set of data. However, if the values of mu I are small, the two statistics can differ quite a bit in a value. Let us do one example and get our idea, clear idea about this. Okay, so we got the following information from this website. And this is the age distribution of the vehicles on the road. And these data were collected in 2022. So what it says, on the very first row, it says the age of a vehicle, and the second row says the probability. That means what is the probability that a randomly chosen car in 2022 is of age between 0 and 4 years. It is 0.11, 11% probability. What is the probability that randomly chosen car in the year of 2022 is of age 4 to 8 years? It is 26% probability. So this is the age distribution of the cars in 2022. Question is, what is the mean age of an automobile that is on the road? So how do you calculate that? This is a group data. So how do you calculate the mean age? And what is the standard deviation of the age of an automobile that is on the road? So in order to calculate mean age, we'll do the following. So I write the table as follows: 0 to 4 years, 0 to 4 years, and then 4 to 8, 9 to 13, so on and so forth. And the last one I'm going to write is greater than equal to 38. And so first I calculate the midpoint of every age group. Midpoint of 0 to 4 years is 2. Between 4 and 8, it is 6. Between 9 to 13, it is 11. And so on and so forth. Now, what about the age group which is greater than equal to 38? So again, since most of the age groups are with the width of 4 years, so I'm going to assume that greater than equal to 38, I'm going to assume also has a width of 4 years. So I'll just add 2 years, calculate the midpoint of that age group. And the corresponding probabilities are the probabilities 0.11, 0.2, 0.19, so on and so forth, 0.42. Mean calculation in this case is expectation of the random variable. What is x? X is the age. Randomly chosen bar. Expectation, we want to calculate expected value of the age will be x times corresponding probability p of x, I call it, and sum over possible values of x. It will be the first one will be 2 times 0.11. Second one will be 6 times 0.26. So on and so forth. Plus the last one I'm writing is 40 times 0.42. This is how we calculate expectation or the mean age. Next question is what is the standard deviation? So you complete this one, you complete this task. What is the standard deviation of the age of an automobile that is on the road? For the calculation of standard deviation, first we calculate variance and then we calculate the standard deviation. So first, standard deviation. What is the standard deviation? Standard deviation is a measure of variability of a random variable. What is the random variable? X, age is the random variable here. Why? Because it changes from one car to another car. That is on the road in year 2022. Standard deviation is the variability of age, and that is square root of variance of x. What is the formula for the variance of a random variable? Variance of x equal to expectation of x square minus expectation of x square of it. Remember, we already calculated expectation of x. So we just need to square that quantity, subtract it from this guy, from this guy, which you will calculate now. Now, expectation of x squared is square the value of the variable and multiply it by the corresponding probability. So the first term would be 2 squared, which is 4 times 0.11. The second term will be this guy 6 squared, 36 times 0.26. The third term will be 11 squared, 121 times 0.19, so on and so forth. And the last one will be 40 squared, 100 times 0.02. So you calculate that and then subtract expectation of x squared. That is your that will give you the variance. And once you get the variance, take the square root of variance to obtain the standard deviation. And this is the distribution, age distribution. If I plot it here, it looks like this, age distribution. And from this graph, you can clearly see that it is a right skewed data. Age distribution is right skewed. Distribution of age is right skewed because you have a longer tail on the right hand side. From the center, what is the center? Approximate center. We do not know exact center now, but approximate center is somewhere here, somewhere here in this region. I move my cursor, I think you guys can see. So this region is the center value. Now, if I ask you what is the mode of the distribution, mode means where maximum frequency occurs. You can say the mode is between 4 and 8 years because that is where you have the maximum frequency. Now, you don't have the frequency, you have the probability. Maximum probability. So at least know where the mode is located. So the mode is somewhere between 4 to 8 years. And what is the median? Median means median is the observation such that 50% of age is below that age, particular age. So if you look at this data set, even table, let's look at it and calculate the cumulative probabilities. So you have 0 to 4, 13. So let's do that actually. Instead of doing it by hand, let's do it in R. Because we'll be anyhow using R in the for solving the next part of the question. So what we have, the probabilities. I'm going to write the probabilities here. One, 26, 119, 12, 14, 105, 102, 0.01. First thing, we check whether the total of these probabilities is equal to 1. So sum of my prob something is not correct. The probability should add up to 1. I did 9. Let's see whether I got it them correctly. 4. At this website. What happened? So when I copied it, maybe I made a mistake recording some numbers. That is the reason age distribution probabilities. So what is happening? The probabilities should add up to 1 if the categories are mutually exclusive. But it is not happening. That means I made some mistake when I was typing up the numbers. And oh, so hang on. I think okay, now it's okay. So this is correct. So when I was typing in R, the very last category, instead of typing in 0.02, I typed up 0.2. That was the reason that the total probability exceeded 1. So now it is perfectly fine. I'm glad that I wrote it correctly. And what I want to show you how to guess what the median is. In order to guess the median, first I calculate the cumulative probabilities. And cumulative probabilities, we call it sum, cumulative sum of my prob. And what I see is that for the third category, you see, for the third category, cumulative probability is 0.56. Third category means age between 9 and 13 years. If you add all the probabilities up to age 9 and 13 years, the total such probabilities will be 0.56. On the other hand, if you add the probabilities up to 4 to 8 years, it will be 0.37 probability. So the median is between 9 and 13 years. Median, the idea of median is the value of the random variable such that 50% of the observations or the 50% of the distribution is below that point and 50% is above that point. So I clearly see that age 9 to 13 includes that median value because it included 0.5 cumulative probability. Now, if you want to calculate exact value of the median, you can do so by this command. But my point is, first you get the idea where the median lies, and then you can exactly calculate using the software. Median of prob. Okay, so it did not calculate median this way because I did not provide the value of the random variable. If I had given the value of the random variable, then it could have calculated. But at least you get the idea where the median is. Where the median. So the median class is between 9 and 13 years. Now let us talk about the application of the multinomial distribution or the goodness of fit test. Suppose that a survey of cars from a US city shows the following numbers. From a US city, we found that we have these many cars. Okay. These many cars, and the age of the cars are like this. So between 0 to 4 years, we have 28 cars. Between 4 to 8 years, we have 35 cars, so on and so forth. Take if the observed data follow the US automobiles age distribution. So these are the observed counts. You can call them as N1, N2, N1, N2. The observed counts. N1 equal to 28. 5, so on and so forth. And how many categories we have? 1, 6, 7, 8, 9, 9 categories. So N9 equal to 8. What is the total count? Total count, let us do that. My count equal to 28. 5, 4, 4, 38. 20, 10, 8. Is 258. Equal to 258 observations, 258 cards were surveyed, and we found out of them 28 are of age 0 to 4 years, 35 are of age 4 to 8 years, so on and so forth. And because the age groups are mutually exclusive, so you can assume that N1 into N9 follow a multinomial distribution. You can write it as follows: N1 into N9 follow a multinomial distribution with N equal to 258. And the success probabilities for the categories are pi 1, pi 2, pi 9. Remember, sum of these probabilities pi 1, pi 2, pi 9 equal to. Now, what do we want to test? We are interested in testing whether pi 1 equal to is same as the age distribution given on this page. Pi 1 equal to 0.11. Pi 2 equal to 126. So on and so forth, and pi 9 equal to 0.02. Alternative is at least one of the above. At least one of the above statements. So if you apply chi-square test, for that, what I need, software will calculate, but at least you should know that the test statistics uses expected value of the ith group. So for example, mu1 is the expected count of the first category under the null hypothesis. Under the null hypothesis, the expected count will be by 1 times n. So it is 0.11 times 258. This is the expected count under the null hypothesis for category 1 or for the age group 0 to 4 years. Let us do that calculation. Time 0.11 is 28.38. And likewise, you can calculate the expected count for other categories. Now, let us calculate the test statistics, Pearson chi-square test statistics. And for that, we'll use chi-square test. Your observed data is my count. Write it as x equal to my count. And probability P will be equal to my probability. Okay, so this is the test statistics. The test statistics value is 105.14. The degrees of freedom 8. And the p value is less than 2.2 times 10 to the power minus 16. Now, so if you test the hypothesis at the 5% level, your p value is smaller than 0.05. Therefore, you reject the null hypothesis. So the statistics. Statistics. Is 105.14. The p value is smaller than 0.05. It's not, and conclude. This is evidence that the underlying age distribution of the observed cars in the city does not follow age distribution of US auto. So that is possible because US automobiles age distribution is a combination of information from all corners of the country. But for a particular city, the age distribution of the cars could be quite different, and that is possible. Some cities are very poor, some cities are very affluent. Therefore, that distribution may not follow the overall age distribution of US automobiles. Okay, now another thing you have seen that we are getting warning messages. Another thing, degrees of freedom is 8. Why? Because there are 9 categories, 9 classes, 9 mutually exclusive categories. So the degrees of freedom of the test statistics will be number of categories minus 1, 9 minus 1, 8. Now chi-square test is valid. This approximate chi-square test is valid. You have large sample. Now, large sample, how do you verify large sample? If the number of expected number of counts for every category is 5 or more. So what are the expected counts for every category for this problem? To get that, I will multiply n, which is 258, with probability. And for group number 8, this is very small, 2.58. Therefore, we get the warning message. At least 5 for every cell count. One way to resolve this issue will be combining some of the categories. So we can do what? We can combine these two categories, age group 33 to 37 and greater than 38. So this is an important thing to note. What would happen to the corresponding probabilities? So we can combine. So our count each group observed data meaning last two categories. Two. The last one will be 33 above. So 28 counts are 28. 45, 45, 44, 38, or and combine with the last two counts. Now, what about the age distribution? Age distribution, the probabilities, corresponding probabilities will be then 0.11, 0.26, So this is the thing, and this is an important concept that even if you combine some of the categories, then these frequencies, they still follow a multinomial distribution with the same n, and the corresponding probabilities will be pi 1, pi 1, pi 2, pi 7, and for the last category it will be pi 8 plus pi 9. Pi 8 and pi 9 were the probabilities for the 8th category and 9th category. Now they are combined together, they are added. Now let us do that calculation again. Let us carry out the test. The new probabilities, my count. So this time, call it my count 2, where I combine the last two categories, 18, and my probability. So here, call it my probability 2, and it will be 0.03. Let us first check the length. And 8. Now apply chi-square test. And this time you do not get the warning message because all your expected counts are more than 5. You can verify it. 258 times my prob is all greater than 5, and test statistics is 95.841. Degrees of freedom is 7. Remember why? Because there are 8 categories, and so number of categories -1 is the degrees of freedom, and the p-value is still very small, so you still reject the null hypothesis. Conclude that the data do not follow the underlying age distribution of the data is different than what is specified under the US automobiles age distribution.